The first topic of review in our algebra review is actually going to be piecewise functions. We're going to be working with them all year in different contexts, but you really need to understand how the graphs of them are made, and then later we'll be talking about specifics to calculus. You'll be asked if the function's continuous or differentiable and those type of things without being able to look at the graph. But it helps to see the graph, so we're going to just practice a little bit. Should be really easy, should be a review. These are all transformations of parent functions that you'll be graphing, so it should be easy peasy to graph. So first of all, remember when a function is piecewise, it just means we're going to chop it up along its domain. So I like to take the place at which it's being, for lack of a better word, chopped up, and I like to put what I call a little invisible fence here. And again, you don't have to, but I like to say at 4, I'm going to be changing and dealing with a different function. I call that a boundary. Then what that means is in here, any number in here gets plugged into this function. Any number in here gets plugged into that one. And you should know that. You should know if I asked you for f of 5, because 5 is in this part of the domain, I would just plug in a 5 here and evaluate. Likewise, f of 0, because 0 is in this piece of the domain of the piecewise function, I would put a 0 in here. A half of 0 is 0 plus 6, so it's nice and easy. All right, so that's the first thing, just knowing when it asks for f of 5 or f of 6 or f of 3, which piece do you put it in? And that's determined by the domain. All right, so a half x plus 6 is just a line, so we're going to graph that. We're going to do a solid dot at 0 because of the equality, the less than or equal to, and an open dot on the boundary. So when I go graph that line, I think I'm just going to use its y-intercept. So I'm going to go up to 6 on the y-axis, 1, 2, 3, 4, 5, 6. And I think I'll just use the slope to go up 1 over 2. Up 1 over 2. So that's going to put me over here with an open dot. And even I could go down 1, back 2, you know, if you like to slope it out a ways to get a really nice graph. But in this piece, this is a line, slope of a half, y-intercept of 6, or you could just plot points and connect them, whatever you like to do, to be honest. However you prefer to graph your line, as long as it's correct. We know that the absolute value graph for loosely, we'll talk about the specifics of y later, but it makes this V shape. Let's talk about some specifics. If it was just y equals the absolute value of x, this vertex would be at 0, 0. However, we have a shift to the right. Remember, it's the opposite of what you would think it is. So the vertex is at 6, and then 10. You did a ton of that in Algebra 2 with the graphing of those. So it's got a vertex at 6, 10, correct? And it opens upside down because of the negative in front of it. So it's going to be an upside down V. And its vertex will be at 6, 10. Now, really, when you graph these, I really want to make sure you get that vertex on there, and I want to know what's happening on the boundary. So because this starts at 4, that's where I'm going to want this function to take off, is at 4.00001. So the first thing at a minimum that I'd like you to do is evaluate the function at that left boundary. It'd be negative the absolute value of negative 2 plus 10. This is 2. We have the negative out front plus 10. I'm at 8. So really what I have is an open dot at, what number did I just put in there? 4, 8. So it'd be kind of, my grid isn't the best. So 1, 2, 3, 4, 5, 6, 7, 8. Probably should have had a little bit better graph there. 4, 8 is actually right here. Anyway, and then it makes an upside down V hitting at 6, 10. So it's going to be kind of up here. It'll be going like this. This is not the best boundaries for this graph, but let's say it's going to stop over here at 9, and we would have 9, 7 sitting over there. So kind of would have been good if I just put an infinity here so I could draw an arrow, but whatever. You get the idea, correct? Now, right here, this would remain open based on the fact that I have less than 4 here and greater than 4 here. Had I put an equal to there, that would have closed the dot up. All right, so just so you know. But right as it stands and the way it was written, that would have an open dot there. So again, on the next one, if I asked you, what's f of 8? 8 falls in this greater than or equal to 1 part of the domain, so I just plug it into here. I would say it's negative the value of 5 squared. And remember, that's not negative 5 quantity squared. It's 5 squared, take the opposite. So f of 8 would just be negative 25. But to graph it, I like to get that boundary on there at 1. I do it in just dotted, just keep it nice, light, and open like that. So little boundary there at 1. I will have a line, correct? You can either see what it does at these two endpoints and connect the dots, or you can use slopes. Again, that's entirely up to you. So because I used slope y-intercept on the previous one, I think I'll just plug in the endpoints of the boundary for the line and go on that route. So on this one, when I put in a negative 2 at the end of the domain, I would have 4 minus 1, which is 3. So I'm just going to go put a little dot there at negative 2, 3. That will be closed due to the equal to bar. And then I'll go put the other end of the boundary in, and I would get a 1, negative 3. So let's go to 1, negative 3, and that will be open. And it looks like that we're ending the domain here at negative 2, so I'll just connect them. So there's my line. And again, like I said, you could have used the y-intercept of negative 2, negative 1, and then done down to over 1, up to back 1. You could have used slope-intercept as well. So again, for a line, you either need 2 points or you need a slope and a point. The next one, this is a parabola, correct? Parent function would be f of x equals x squared. That makes this nice parent function that hits at 0, 0. However, this minus 3 here will move it 3 to the right, and this negative will flip it over. So its vertex is going to be at 3, 0. That's important. You need to get the vertex on there. So 1, 2, 3, 0. I will check that on your first test, that when you graph, that if it is an absolute value or a quadratic equation, that you get that vertex on there. This opens upside down, but I'd be careful with just connecting. Like, here's what I'd say. Oh, you might be tempted to just take this and go like that. Don't do that. You should really make sure that that piece of the function indeed takes off at negative 3. So let's go see what happens when I put in a 1 here. Because again, that's where I'm taking off on that boundary. My parabola will be to the right of 1. I'd have a negative 1 minus 3 quantity squared. I'd have a negative negative 2 squared, which would be the opposite of negative 2 squared, or 4. So you'll notice when I go graph this, I'm actually at 1, negative 4. So it didn't, you got to be careful with getting sloppy, but then you can just kind of go like that. And last up, I have a 3-part piecewise function. I have a line, y equals mx plus b. I have a parabola because of the quadratic, or x squared. And then I also have another line that's horizontal, because it's really just the line y equals 9, or 0x plus 9. So then I have a horizontal line. So I'm going to have 3 things pieced together on 2 boundaries. One of the boundaries is 1. Again, you don't have to put the little dotted line in there. I just like to do it. I call it a fence. And then I have another partition here of the domain at 4. 1, 2, 3, 4. I will make a line to the left of 1. First of all, I'm going to see what happens at 1. When I put in a 1, I get a 0 out. So that line, open dot, again because of that less than or equal to, this has a slope of 1. So it'd go up 1, over 1, or down 1, back 1. But it should have, it should be going uphill as you look at it from left to right. So there's my first piece of my piecewise function. Then I have a parabola that's been shifted 1 to the right. Its vertex will be at 1, 0. This is equal to, so that's going to fill in that dot. Okay, in the past, by the way, I've had kids who do that. That's not notation for anything, so we won't be doing that. It's either open or it's closed. So make sure you clearly make that known to me when I'm grading. All right, what else do I need to do? I told you I like to know where that vertex is. Well, the vertex is at 1, 0, and that's on the boundary. It opens up, correct? So let's see what happens at 4. It'd be f of 4 will equal 9, or I'll be at the point 4 comma 9, or 3 squared. So let's go 1, 2, 3, 4 up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, correct? That will be open. And this is a parabola. And remember, it's symmetrical about the vertex. So it would swing down, and then had it not been a piecewise function, it would have continued this way. But it went to a line on that piece. Next, I have a horizontal line at 9, and it says greater than or equal to. So it'll close it and head on out. So you'll notice this last graph is the only one where I can trace its path. This is loosely. We'll have a very calculus-based definition of continuity in our first chapter, but loosely. If you don't lift your pencil, we say it's continuous. As you move from left to right and you do not lift your pencil, now, what's going to happen later in the year is we're going to be talking about continuity because it's the hypothesis for a number of theorems for us, and you won't be able to see the graph. So we're going to have to know what causes us to lift our pencil without being able to look at a graph. But for today, you're just going to graph them, and if you don't lift your pencil or pen or writing utensil as you go left to right, you're continuous. You'll notice for the first graph, I had to lift my pencil right here because that's open. I could have fixed the continuity or made it continuous if I had just done either. If you look at where I'm erasing, had I either done this or this, it would have filled in that dot and I wouldn't have had to lift my pencil. So that's kind of nice. By the way, I left the domain here on this first line. I think, our domains are going to be not restricted so much. We'll be going to the infinities, but I should probably do that. So this function's continuous on its domain. Okay, then not continuous. The next one is also not continuous on its domain because right here I've got a little 1 unit jump. We're going to later call that a jump discontinuity, but for now I lift my pencil. And this one right here on its domain, I'd never lift my pencil. So this is the only graph that's a continuous piecewise function. All right, next up. So topic B, not knowing your unit circle is a huge issue in here. So if you know you don't really know it, you might even want to get on the internet and Google, and they've got a bunch of like practice worksheets. Maybe I'll even put some in Schoology or something, but we don't work with degree. You should put your calculator in radians and never go back unless you're in AP Physics. Then you kind of have to toggle between the two modes throughout the year. But we're going to be working exclusively with radians. You'll need to know the exact cosine and sine for the angles below. All right, and there's a reason why we know these exactly and know others, but I'm lumping two sections together. So I'm going to hope you know what a radian is. I'll discuss it in class, but for this video, if you're absent, I'm going to cut that out. And I would hope that you know that the exact ones come from the fact that they're parts of 45, 45, and 30, 60, 90 right triangle ratios. So let's go label these as we go around over here. This would be considered 0 radians. And the way I like to label them is when you're first teaching it, but you've done this in Algebra 2 and in pre-calc, so you probably have it memorized, but this is 0 radians, and then I like to cut them in fourths. So this would be 1/4 pi. This would be 2/4 pi, or pi over 2. Over here would be 3/4 pi, and over here would be 4/4 pi, which is just pi. So you'll notice halfway around the circle is pi radians. Really the word radian means radiuses. So it means if I were to take the radius of this circle And if I were to cut a piece of string that's that long and then use it to measure around the outside, it would take pi of those radii to get over to here. And pi is about 3. Notice I did about 3 of these, 0.14. So when we talk about radians, it's really just how many radii would stretch around the circle to get to that angle measure. So there's my 4/4 pi, and my 5/4 pi, and 6/4 pi, which is 3 pi over 2, and 7/4 pi, and 8/4 pi, also known as 2 pi. So I go around in fourths first, and then I go around in sixths. Sixths, it's hard to say. 1/6 pi, 2/6 pi, 3/6, which is a half, 4/6, which is 2/3, 5/6, excuse me, 5/6 pi, or 5 pi over 6, and 6/6, which gives me the pi, 7, 8 pi sixths, 9 pi 6, which coincidentally, and then 10 pi sixths, and then 11 pi sixths. So that's how I label all of mine. You should have a really good concept of where those are. So if somebody asks you to find 7/6 pi, you should go, well, pi is 6/6. It's just one more notch around the circle. Also, we need to know the cosine and sine. So cosine of an angle is the x value, and the sine of an angle on the unit circle is the y value. Now, why would that be? Like, why is cosine the x and sine the y? And it has to do with this. So if I drop a right triangle down here, correct, and I call my angle theta, and this is indeed the unit circle, which means its radius is 1, and if I move over x units and up y units to cut out that angle, remember your SOHCAHTOA stuff that the sine of an angle is the opposite over the hypotenuse. You'll get that the sine is actually the y value. And cosine is adjacent over hypotenuse, which in this scenario would be x over 1, or just 1. So that's why when we say that cosine's the x and sine's the y, right? We're just parameterizing them is what it's called, but we're using an angle to get there. But it comes from SOHCAHTOA. So now let's talk about the way I remember these. First of all, at the quadrangles or at the endpoints, those are all the zeros and ones. So let's do those first. This is 1 to the right and 0 up. So cosine 0 is 1, sine 0, 0. This is 0 over 1 up, so consequently cosine pi halves is 0 and its sine is 1. You guys have done this enough. If you're not good at it, you're going to need to practice more than what I give you, but I'm assuming the majority of you guys just need a tiny little bit of a refresher. So there's my quadrangle ends, and then for the other ones, I always just memorize that the sine of pi over 6 or the sine of 30 degrees is a half. Then I go to this one and I say, well, this one's the flip. The other part of it is root 3 over 2. So I just do that. I know you guys make reference triangles and stuff. That always works. It's great. But once you do enough of them, you should really just be able to think it out. And by the way, remember that this is the y value. So sine here, it does look like it's about halfway up, where the cosine, or to the right, the x, looks almost all the way, and root 3 over 2 is pretty close to 1, so it's kind of works out that way too. And remember, the other one is just root 2 over 2. And then for all the other ones, it's just a matter of changing the SIGNS as the signs. So over here, I'm to the left and up the same amount. So it's the same value over here. It's just I've gone left and up instead of right and up. And that holds for all of these. It'll be negative root 2 over 2, comma, positive root 2 over 2. They're all to the left and up. Now when I go down here, they're both negative. So right here, I would have, it's actually the same as the pi 6. The only difference is that I'm to the left and I'm down. Where over on this one, I'm that same amount to the right. I'm at root 3 over 2, but it's down. So you should be able to fill in the rest of those just by thinking them through with the signs and the quadrants. I'm not going to give you the traditional unit circle quiz. What I'm going to do is give you one of the 6 exact trig ratios for random. I will ask you to give me one of the 6, and I say 6 because we've got sine, we've got cosine, but remember we also have tangent, which is their ratio, so you might want to write this down if you don't already know it. Again, take what you need out of these first days of algebra review. Cotangent is the reciprocal of tangent. We have secant, which is 1 over cosine. The way I remember those is I think St. Cloud. The S's go with the C's and the C's go with the S's. So consequently, cosecant is 1 over sine, or its reciprocal. So you should know those and how to set them all up for whichever ones I ask for. So I'm going to just do a few of these in class. I have you go through them all on your own, but if you're watching these videos because you're absent, I'm not going to go through the whole thing. Sometimes I say make a helper circle if you need one. Cosine is the x at pi. I'm negative 1 comma 0 over here, so cosine pi is negative 1. But the sign there is 0. The tangent is sine over cosine. That's 0. When I get a 0 in the denominator, we say it's undefined. All right, so first row's done, easy. Make a little helper triangle, right? Think of this as sine over cosine, y over x, or sine over cosine. You need to go to pi over 2, bam. You need to write it or think of its coordinates. It's 0 to the right and 1 up. I need to do the sine, 1, over the cosine, 0. This would be undefined. Or a lot of times in calculus, we start using what we call the phrase DNE, or does not exist. All right, let's go do one a little bit harder here. Sine of 3 pi over 4, you need to know where it is. So it's one of the pi fourths. It's not 4 pi over 4. That would put me right here at pi. It's 3 pi over 4. So it's right here at that split. Remember, that's a pi fourths. Those are all root 2's over 2's. Any of those pi over 4 angle increments have this ratio for both sine and cosine. The only thing that's going to change is the SIGN of it. And this over here is to the left and up. So it's to the left and up. So the sine of 3 pi over 4 is exactly the same as the sine of pi over 4. They are both positive, and it's root 2 over 2. And if you're thinking, she's going so fast, this should be like the 3rd time you've been taught this. So I'm really just trying to get you in the flow again. So again, where is 2 pi over 3? Right? Well, it's 4 pi over 6, right? It's not quite 3 pi over 3, so it's not to pi. So we kind of know it's this guy over here. This guy over here has the exact same as this one over here. It's just to the left and up instead of to the right and up. So let's write this one down. I always remember, I memorized that this first pi over 6, there's a half in the bottom right, which puts a half in here, and we're at 3 over 2 here. But this is to the left and up. All right, so let's do the tangent. Tangent is sine, which is y, we're at 3 over 2, over cosine, negative 1 over 2. Don't leave that, that's a complex fraction. We'll multiply by the reciprocal, and the 2's will cross out, and I get negative root 3. I think we'll just do one more of these. Like, you should have this down in class. We'd kind of keep cruising along, but let's go try a secant. Secant will be 1 over cosine, which means I need to find this angle on my unit circle, think of the x value there, and reciprocate it. So let's go to my helper circle. 11 pi over 6 is almost 12 pi over 6. So it's just like 1/6 pi, away from completing the whole circle. I go all the way around to here. It's got the exact same coordinates as this guy. except for the signs. So again, the way I remember the 1/6 is there's always a half in the far right, or the sine of 30 degrees is a half. That's just kind of drilled into me. It actually comes from a Big Bang Theory episode. We can talk about that in class, but for the video, we don't get any of that fun stuff. I just got to get her done. All right. So over here, I'm still to the right, so I will have the same x value. You can see it. They're both the same amount over to the right. This one's down a half. So I need to do 1 over its cosine, the x value, which would be root 3 over 2. So multiplying by a reciprocal or reciprocating, I get 2 over root 3. I'm totally fine with you leaving that, by the way. We don't need to rationalize denominators in here, but if you choose to, that's fine. I would leave it, though, in case you do it wrong. That's all I'm going to do with those. All right. Next page. Solving with our trig. So first thing we're going to do for the solving is we need to isolate the sign. We'll divide by 4. Whenever you're solving for something, you need to isolate it first by getting rid of everything that's in the way. To get rid of everything that's in the way, we do the opposite operation, or the inverse operation is a better word. So now I need to unsquare. So that would mean I take the square root. Remember, when we do that, we get plus or minus the square root of 3/4, which would equal plus or minus root 3 over 2. So I'm looking at one full term around the unit circle where the sign is root 3 over 2. So let's talk about where we're looking. Right here, remember, sign is a half. So we're not looking at the pi sixths. That's not root 2's over 2's. That's not the pi fourth. We're going right here, right? And we need the sign to be root 3 over 2. So this is my first answer. My first answer would be at pi thirds. My next answer would be over here, where I also have a sign that's positive. So that would be at 2 pi thirds. My next one would be down here, and you might be, I don't know what one that is. Remember, you can count them out. This is 6 pi sixths, 7 pi sixths, 8 pi sixths. And remember, right in the split is the pi fourths, so we don't worry with that one. So this would be 8 pi 6, or 4 pi over 3. That would provide one of the negative signs. It's below the x-axis. And my other one is right here, right, at 10 pi over 6, which is 5 pi over 3. So those would be my 4 angles that would solve that trigonometric equation. And last one, I was hoping I could do this in under 30 minutes. So I know it's a lot, but we just kind of getting some basics down before we start our calculus. You might be tempted on this one to divide by cosine. Don't do that. All right, we lose solutions. So in this class, starting now, to solve any complicated equations. That one up there wasn't very complicated, but we get one side equal to 0, and then we factor. All right, so just kind of, and if it doesn't factor, then we'll go use our graphing calculator, and we'd put this in the y equals, and we just calc 0. So there would be no need for us to do anything fancy. But this one, if I didn't have a calculator, which I don't, this whole first unit's no calculator, we'll factor it. So we've got a 3 and a cosine in both pieces of the sum. And then I'd get a 2 sine x when I factor that out, plus 1 that equals 0. For a product to equal 0, one of the 2 or 3 or 4 parts must be 0. I can't multiply to get 0 if 0 is not in there somewhere. So this means that either 3 times the cosine of x is equal to 0. If it's not, then 2 sine x plus 1 has to equal 0. So we'll solve each of these separately. So this would imply, or dividing both sides by 3, I need to know where on the domain, I didn't give a domain here. Let's say on this one we're going, just because you should always watch domains, let's go 0 to pi. All right, cosine being 0, cosine's 1, then it's 0, then it's negative 1. Remember, cosine's the x value. Okay, so this would be pi halves would be one solution. And you might say, and 3 pi halves also. Yep, if my domain had been to 2 pi, I'd include that as well. But I'm just restricting you to the top half of the unit circle. So we'll leave that one there. So always watch those domains. Solving this one, I'd have twice sine x has to equal -1. Sine x would have to equal -1/2. So that means I'm below the x-axis, not any of this, right? And remember, it's this guy that has the sign of a half. So I just need to be 1/6 below in both directions. So let's think about that. This is 6 pi 6. One more little turn would be at 7 pi over 6. And you might say, in this guy too, one back, 11 pi over 6. It would be, had my domain gone to 2 pi, but watch the domain. It didn't, and actually this guy's not in the domain either. So I wouldn't have any solutions. So I'm going to go make this 2 pi, just so I can, now I'm going to have to add a 3 pi over here. I just want to have some solutions, guys. Makes me feel good. 7 pi over 6 and 11 pi over 6. And I'm going to quit there. It's at exactly 30 minutes. Have a good one.